welcome back. And today we're back to working on the Centurion. Most notably, we're going to be working on this power supply right here. It left us in a bit of a lurch last episode. But first things first, a couple episodes back, we were working on the Bendix G15, and we discovered that the rotating drum memory unit was very heavily crashed. Now, this Bendix G15 is on loan from Bob over at System Source Museum up in Maryland, and it just so happens that Bob happens to have another Bendix G15 on display up there. He pulled the cover off of it, took a look inside, and that drum is not crashed. So we're going to perform a drum swap. I'm going to take the drum that we removed out of this G15, throw it in the car, and drive all the way up to Maryland, where I'm going to put it into their machine that is on display. And I'm going to take the drum out of that one, bring it back here so we can get this machine up and running. The reason I'm telling you all this is because that day is going to be October 23rd, and we're going to be having an open house at System Source Museum. So if you find yourself bored on October 23rd, come hang out with me and Bob and everybody over at System Source Museum. He's got an unbelievable collection of machines. Come hang out with us on October 23rd at System Source Museum. I put a link and all the information in the description below. But that has nothing to do with what we're actually working on today. What we're working on is this power supply. This power supply pumps out 4 voltages, -12, +5, +12, and +24 volts. The main computer only uses 3 of those. It uses the -12, +5, and +12. And the power supply supplies those 3 perfectly, so I thought the power supply was working just fine. But in the previous episode, we tried to get this floppy drive installed. And we actually got it on this really cool tray that pulls out. And I put the Finch right next to it, which is an 8-inch hard drive, and the Finch power supply, which means that powering up the Finch is not going to be any problem at all. We got the power supply right up there. All we got to do is get AC up to it. This particular floppy drive came from Mark over at CuriousMarc, and if you are not aware of CuriousMarc's channel, go check it out immediately. He does some amazing restorations and has just one of the coolest labs I've ever seen. I had an absolute blast hanging out with Mark and his team, and Mark so graciously donated this floppy drive to the Centurion, which is the correct CDC floppy drive for this machine. And we've even got it mounted in the front panel, just like Centurion used to mount it back in the 1970s. So we're doing great, except that we need to power it. The floppy drive needs +24, +5, and AC. Now the AC is no problem. Like I said, we've got that up there for the Finch power supply. We'll just tap off of that. +5 is also no problem because we know that this power supply is putting out a ton of +5, and we can really just kind of take that from anywhere. The +24 is the issue. We know the power supply puts out +24, but we can't find it anywhere. I checked all of the connectors on the front, every combination that I could think of, and I discovered J1 and J2 are the connectors that are designed for a floppy drive. They have AC 120 volts on them, they have +5 volts on them, and they should have +24 volts on them. So I started tracing that back, and it turns out that the pass transistor is never getting the signal to pass voltage through it. The pass transistor is just turned off all the time. That means that we have a failure somewhere on this regulation board over here, which is a stack full of 723 regulator ICs. So I need to get into the thick of it with this to figure out where our fault is. But before we get that far, since I have the power supply out here on the table, I thought it'd be a good time to try and wrap my head around what kind of power supply it is. This is what's called a ferroresonant power supply. Now, if you're not familiar with power supplies, or even if you are familiar with power supplies, the word ferroresonant sounds like I made it up on the spot. Sounds like some kind of MacGuffin that they would say in a sci-fi movie, but I promise you ferroresonant is a real thing. And actually, the power supply itself is not ferroresonant, it's just the transformer here. And so I started trying to figure out what exactly a ferroresonant transformer was. And in order to understand that, I needed to start by trying to figure out what a normal transformer was. And transformers are essentially magic, wizardry, sorcery. That's what's going on here. But the construction of a transformer is fairly simple. You just have a magnetic core, usually made out of iron. Then you have a coil of wire around one side and a coil of wire around the other side. Now, before we go any further, I just want to say this is an area of electronics that I am very weak at. I don't grasp this as well as I really should. But I'm going to try and boil it down as simple as possible and explain it as best as I understand it. I know that a lot of you guys watching are going to be a lot more familiar with the concept of transformers and ferroresonant transformers. So hop in the comments and let me know how accurate I was or how completely off the mark I was. And anybody else who is watching, definitely go check out the comments for fact checking. Don't take anything that I say here as gospel. I'm mostly just guessing my way through this. But a transformer physically is constructed fairly simply. You have the magnetic core, coil wire around one side, coil wire around the other side. We'll call one side the primary, the other side the secondary. So we'll put an AC voltage on the primary, and you have a sine wave that goes positive and then negative. As that voltage passes through the coil of wire, it induces a magnetic field into the iron core. That magnetic field travels around the iron core over to the secondary. Now, the only thing that's connecting the primary to the secondary is this magnetic field. The actual coils of wires are completely isolated from each other. It's just this magnetic flux traveling through the iron core that makes it over to the secondary. And as it travels through that secondary coil, it induces a voltage into it. Now there's a little tricky things going on here, and this is where we're getting into like strange material sciences stuff. Again, stuff that's way over my head. Now the secondary is going to have a load on it, so it's going to induce a flux in the reverse direction. And the heavier the load, the more reverse flux there is, which means that there needs to be more current coming through the primary to overcome that reverse flux from the secondary. And they actually demonstrate that with a little diagram here like this. You have this region on the left where as you put more current into it, you get more voltage out of it, and it's really linear and really nice, and that's where a transformer is supposed to live. And then you get up to the spot that they call the knee. When you get to that knee, you can see that it flattens out. You don't get any more voltage, but you start getting a lot more current. So you don't want to push your transformer into this region because now you're just generating heat. So you want to keep the transformer in that nice linear region over on the left. That's moderately understandable. That's how a transformer works. Every machine in this room has a transformer in it, and it's really not super complicated, even though I have a difficulty time understanding it. But when you get to ferroresonant transformers, it goes off the rails. The initial construction is very similar. You have a core, you have a primary, and you have a secondary winding. Now things start to change when they add in an additional secondary winding called a tank circuit. The only thing this winding hooks up to is a capacitor. We can actually see that here. This is the capacitor that's part of the tank circuit on this ferroresonant power supply. So what does this tank circuit do on a ferroresonant transformer? Well, that tank circuit is essentially just an inductor and a capacitor, and an LC circuit is an oscillator, and it has a resonant frequency. So you can do the math and figure out the henries of the coil and the capacitance of the capacitor, and it'll come out to some frequency that it resonates at. When you have a voltage coming into your primary, it's going to generate magnetic flux that's going to travel down into the secondary, and it's also going to travel down into the tank circuit. Now the tank circuit is going to start oscillating, and when it does this, it's going to line the waveforms up in such a way that the secondary gets thrown straight into saturation. Now if you push the secondary into saturation, the primary is also going to go into saturation, right? Well, that's bad. We don't want the primary to go in saturation. So we want the primary to live in that linear region, and we want the secondary to live in the saturated region. So we separate the two with what's called a magnetic shunt. So there's just this kind of magnetic space that sits in between the two. And you can actually see that on this transformer right here. That's this open space between the primary and the secondary coils here. So this magnetic shunt, what it does is it takes some of that flux and allows it to circle around within its own location. So some of the pushback secondary flux that's coming out of the secondary coil in the tank circuit circles through the magnetic shunt and just makes a big circle on the bottom side, never influencing the top side. Now, of course, the same thing happens on the primary side as well. So it becomes very important to engineer how much flux makes it through the shunt and how much flux doesn't. And they do this with air gaps and other crazy engineering things. But the idea is that the primary is never in saturation and the secondary is always in saturation. So why would you want to do this? If you go into saturation, you're just causing it to run a little hotter. Well, if you design it and engineer it to withstand that heat and be okay with that, you receive a really interesting property here. And we can actually see that if we rotate this thing up and take a look at what the input voltage on the back says. It says 90 to 130 volt input. That is a 40 volt range of input that will give us a constant 5 volt output. Now that's really weird because transformers take an AC voltage in and they transform it on the way out. But whatever you get on the outside is pretty much directly proportional to what you're putting into it. But this can take a 40 volt change in input voltage and still give us an extremely stable output voltage. That's because our secondary is living in that saturated region. You can change the input voltage pretty dramatically, and the output voltage is only going to change ever so slightly because we're just moving left or right along this flat part of the curve over here. Really brilliant way to get really stable voltage out of it. So you can have a very fluctuating input voltage. And this can happen if you're in an environment that has a huge load on the electrical system. You can get a lot of electrical drag, essentially. A lot of people at VCF Midwest were actually saying that they were reading something like 90 volts on the mains AC, and they were popping breakers and machines were not running or they were having difficulty running, and this thing would have just taken it with a plum. It would have had no issue whatsoever with a 90 volt input. The Hawk drive would have had a million problems with it, but the actual computer would have run just fine because it has a ferroresonant transformer in it. So it's using a lot of magical wizardry to move magnetic flux around in such a way that we get an extremely stable output. Now, when that output comes out of the secondary, it's still AC. We have to rectify it. So it has to go through a full bridge rectifier, and then we need to smooth it out and regulate it. So how do we regulate that voltage that's coming out to give us a consistent smooth 5 volts the entire time? Or in our case, a consistent smooth plus 24 volts the entire time? Well, we can actually see the 4 individual regulator circuits on this regulator board right here. Each one is kind of split up in its own little separate section, but we're only going to focus on the plus 24 volt rail now, and there are no schematics for this power supply. So I sat down with just a photo of the front and back of it and started trying to trace it out, and I've come up with some semblance of a schematic, and I think I'm starting to hone in on where our problem is. But the 723 is a pretty interesting IC. What's important here, though, is that we have a reference voltage coming in. We have a sense voltage coming in, so what our output is. It's going to compare that versus the reference. It's going to change that output up or down based upon the difference between the two. And so we're not seeing anything. We're not seeing any change on that V out. So we have a short or a failed component somewhere. In order to find that, we have to kind of understand what that 723 is hooked up to. On the far right, we've got the pass transistor. This is a 2N3771. This is a big stonking transistor on the massive heatsink over here. We have a high amount of voltage coming into one side of it, and then on the other side of it, we go out to the plug over here that's going to supply the plus 24 volts to our load. We also come off of that, go through a very tiny resistor, 0.18 ohms as best as I can tell, and then we cut over into a current source, so that way we can tell that there is some actual current passing through it. And then we have an interesting kind of feedback path that ultimately makes its way all the way over to the inverting input of our 723. This is that one input of our comparator. The non-inverting input is coming straight out of the reference. So it's comparing our reference versus our inverting input, and if they're different, it's going to change the output. The output goes to a 2N2102 that then ultimately goes to the pass transistor. So that's how we're kind of getting a little bit of feedback from our output. But all of that is currently sitting at 0 volts, like nothing is happening on that side. So if we look at the 723, there is a little signal here called frequency compensation. And I measured that at 0 volts, and it should never be at 0 volts. So that tells me that the 2N222 transistor that it's connected up to is pulling that frequency compensation to ground. So the fault is somewhere around Q10, Q11, and CR21, this collection of components right here. So that actually gives me a direction that I can start testing in. So I've been sitting here in this chair spewing verbal diarrhea at the camera for about 30 minutes now. Hopefully I'll slice that down to something much more manageable in post. But I think it's time to actually pull the multimeter out and start testing things and seeing if we can find our fault, because I am fairly confident that we've honed in on it to about 5 or so components. So let's start checking stuff. All right, I think I'm honing in on the problem. I got the working power supply out so we could check some voltages across it, and I've been checking all across it as well. So I mentioned that I think it's not right that our frequency compensation here is at 0 volts. And if we check backwards across that, Q10 here has 0.6 volts on it, turning it on. So that's going to pull our frequency compensation to 0. So if we trace that back a little bit, that means that Q11 here is turned off. And it should actually be turned on. We want Q11 on to pull the base of Q10 down to 0 so that our frequency compensation can come back alive and our 723 can all start living. But with Q11 turned off, we need to look at why it's not turning on. So if we follow that back, we get to this 20 volt zener here. And if we check on the other side of that 20 volt zener, we're getting 13.6 volts or so, which is very much so not correct. We can actually see that right here. That's CR21, which is going to be this one right here. So if I check on that side of it, you can see right there, it actually shows 13.4 volts this time. But that's not enough to kick that zener off, so that's not great. So if we follow that back, it moves us all the way over to Q1, which is over on this side of the section. There's just some other stuff going on here that has to come up first in order for the 24 volt section to come alive. And we're seeing that right here with Q1. Now, coming into the collector of Q1, we have 13.6 volts. We can check that right in there like that. Yeah, there we go, 13.4 volts. So that seems really strange. We should either have 20 plus volts to turn the zener on, or we should have 0 volts. And if we check the base of Q1 here, you can see it's at like 26 millivolts. It's still letting some current flow through it. And I think that's what we're seeing. I think we're seeing Q1 here be leaky or marginal or something like that. But I think that's our culprit over here, this little Q1 right here. So I'm gonna work on that. I'm gonna probe around a little bit, and then we'll flip the power switch back on and see if our 24 volt rail comes back to life. All right, we worked on this pretty late into the night last night, and I think we've got it cracked. So there was a bit on the schematic here. This is the 24 volt section over here, and there was a bit of it that speared off towards the section over here. The 24 volt section will not come up unless the 5 volt section comes up and is good. And so if we follow that down to here, we get to Q1. But Q1 must be conducting some because it's pulling this kind of midpoint down. And so if Q1 is conducting, that means that Q2 is not conducting and the base of Q1 is being pulled high. So we can actually confirm a little bit of this if we check the base to emitter voltage of Q1 and Q2. So if we check the base to emitter voltage of Q2 here, we see something that's really curious. That's 0.68 volts. That is perfect for Q2 to be conducting. But if Q2 is conducting, that means that the base of Q1 must be pulled to ground. We can see that that has to be happening. So if we check the base of Q1, we get 27 millivolts. For a 2N2222
27 millivolts is actually enough to get the transistor into the linear region and start to conduct a little bit. So Q2 should be conducting, but it's not pulling the base of Q1 to ground, and that's really curious. So we actually replaced Q2 because we thought it was faulty, but exact same problem. That's strange, and I don't think we're going to be able to see it with the multimeter here. So we pulled out the scope, we started probing around, and we decided to check this junction right here. This is the R3, R1, CR4 junction. This is kind of a node that's feeding directly into the zener that goes to the base of Q2. And if we turn on the scope here and check that out, look at that. We can see a very specific spike happening, ripple or something of some kind. That is not great. So I think what's happening here is that Q2 is conducting most of the time, but whenever it spikes ever so slightly here at that node, Q2 stops conducting because it's dropping just enough for the zener diode there to turn off. So we're getting this kind of like rhythmic pulsing of Q1 just barely conducting, and that's pulling our junction point that feeds into Q11 and Q10 down just enough to stop those from working correctly and smashing our frequency compensation. So if we look at this junction right here between R1, R3, and CR4, there is a little capacitor there, C2. This is a 22 microfarad capacitor, and it's supposed to smooth out pulses like this. I actually have two leads hooked up across that 22 microfarad capacitor. It's this one right down here. And this is another 22 microfarad capacitor. And if I just put this in parallel to that, check that out. Our little pulses go away completely. And I mean, we can check again with this. It's not gonna make any difference though, because we're still gonna see that same 0.68 volts across there. But if we check the base on Q1, look at that. All the way down to 3 millivolts. It was at like 20 millivolts before. So Q1 is definitely not conducting right now, which must mean that everything else has sprung to life. So if we come back here and check on the connector, look at that, 25 volts. Now it's a little high, we'll have to adjust it with the control potentiometer right over here, but we're nailing it. Our 24 volt rail is back. We figured it out. It's just a bad capacitor, but it's not the bad capacitor that I would have suspected. I would have suspected one of these big jobbies down here, like C1 or this big 4700 microfarad job over here. But it just turned out it was the smallest electrolytic on the board. And if we just disconnect our little parallel cap here, we get our pulses back, showing us that that capacitor is indeed bad. So I'm gonna go through and replace this capacitor, and that will bring our power supply up to full working condition. All right, power supply is fully back up and working. We have our 24 volt supply. I soldered in our new little capacitor down here, and it's fully working. I didn't think I was gonna get there. I wanna thank MX Shift, Chris, Mutz, everybody that was in the voice chat and helping me out on Discord. You guys rescued this project. I could not have gotten there on my own. It was absolutely a team collaborative effort. So thank you all so much for that. It was actually a ton of fun diagnosing this with you guys. But all we need to do now is take our voltages, our plus 24, our plus 5, and our ground, and wire it all the way up here to this floppy, and then we're gonna be good to go. But before I dive into that, there's one thing I want to address, which is I know there's gonna be somebody either in the comments or somebody somewhere is thinking that I should just recap the entire power supply. And I'm not gonna do that. And there's a couple of reasons behind that thinking. First of all, the other caps are fine. I checked Ripple on them and they look totally okay. So I don't want to unnecessarily replace capacitors that are not bad, even if they might go bad in the future. Well, everything might go bad in the future. I don't think we should replace every single component because it has the potential to fail. If it's working perfectly now, and we know that it is because our +5, our +12, and our -12 have been running the computer flawlessly for years, if it's fine now, there's no reason to replace those capacitors. The second big reason is yes, if I had just recapped this entire PCB here, it would have fixed our problem, but I wouldn't have known why it fixed our problem. Because I dove into trying to figure out what exactly was going on, we discovered a couple of really interesting things. First of all, we now have a schematic, so we can use this as a foundation to troubleshoot other parts of the PCB. Also, I learned a massive amount about power supply construction. There's so many things that I never would have thought of that I learned through this. So by actually going through and troubleshooting this machine and troubleshooting this power supply and figuring out exactly what was wrong and replacing just that component, we learned so much more than we would have if we'd have just sat down and recapped the whole thing without even thinking. So that, I think, is the real value in trying to troubleshoot electronics like this. I learned so much throughout this process. All right, I'll get off my soapbox now, and I think it's time that we throw this back into the machine and get it wired up, and I want to see this floppy drive up and running. And that's actually going to be a little more difficult than it seems at first, because after we get power to it, this floppy drive is set up not for a Centurion, but for an HP. So I'm going to have to change a lot of settings on it to get it to play nicely with the computer. So that's going to be pretty interesting, I think. First things first, let's heft this power supply back into place, and it's a beast for sure. That Ferroresonant transformer weighs a ton, but I managed to get it all lined up and bolted in correctly. And next we'll start on the wiring, and I'm actually going to use separate plugs on the wires. I'll solder them in the middle so I can disconnect the drive power without having to unplug the cable from the drive. The reasoning for this is because I don't have the appropriate Molex connectors. I have the pins, since that's standard stuff, but the specific connector shape I don't have on hand. For the one that goes into the back of the floppy, I have one on the way. Thank you so much, Glenn. But I haven't found the appropriate one for the power supply just yet. Either way, once they show up, I can pop these pins into the connector easy peasy. But for now, I think this will work just fine. For AC power, I'm going to pull it off of the same power strip that the Hawk is plugged into. That way, all the drives can be switched on or off separate of the computer itself. I need to make a custom cable that will power the floppy and Finch, because I want to be able to power them up separately from each other. And this is the cable I made. AC power comes in and goes straight through to the floppy connector. Midway though, I tap off the hot and run it over to a switch. Then from that switch, I circle back around and go to the plug for the Finch power supply. This way the floppy is always powered up, but the Finch only powers up when the switch is flipped. Next up was setting up the floppy drive itself. Unfortunately, instead of dip switches, it has these little make or break jumpers that are just a nightmare. Fortunately, I didn't need to change too much. The HP setup these drives were in used the drive select signal to also load the head. However, the Centurion has a separate drive select and head load signal. So I had to change about 5 different jumper settings to get that set up correct. I just created a solder bridge across the ones I had to remake, and that seemed to work perfectly. Okay, I've got it all back together. The floppy drive mostly needed some changes with head load, I think, but I think I've got it all set up correctly. I did a couple of preliminary tests of just the floppy with the diag card, and it seems to be mostly working. I haven't tried it with the Finch yet, so that's the next step. I've got the Hawk spun up, I've got the floppy on, but I haven't turned the Finch on yet, so I'll go ahead and flip the power switch for it. It's starting to spin up. It should do its self-seek test. It did its self-seek test. Let's see if we can get into the operating system. We want to see max disk equal 3 here, I believe. That's good news. We got max disk equal 3. Okay, so 08, 23, 84. When it says CRT0 ready, we're fully in the OS, and we'll do a .sta at that point. And I heard it load the floppy. Now the floppy isn't formatted or anything like that, so let's make a new floppy. We'll do a s.newDisk And we want that to be disk number 2. And it's guarded, because of course it is. So let's do a .noguard2. And then we'll do a .s.newDisk again on disk number 2. We want to call it Fusagi. And yeah, we're ready. Now this is only a single-sided dual density floppy disk, so we're only going to get about, I think, 96 tracks total. Now I can see that the actuator on the floppy is moving. It looks like it's formatting it correctly, so hopefully this all goes smoothly and we have a working floppy by the end of it. Okay, looks like it finished. Let's do a .sta again. We should see Fusagi in here. All right, that's good news. If I do a .dir2, we should see the directory of the floppy. It only has the Whipple in it and nothing else because it's a freshly formatted floppy. We should see how many tracks we have. We have 92 available and 3 used. So 96 tracks, there we go. This is the real one. Can we still read the Finch? .dir3. Yes! So we don't have a ready conflict going on like we had with this floppy drive before that I had to change a setting on. So it looks like I've got all of the settings correct on the Finch and the floppy. To get through all of the directory listing here is going to be madness. But if we go back to the status, we can see it looks like there's 4 drives, but there's actually only 3. Data 6 and Soft Term are the 2 platters on the Hawk drive. Fusagi is our floppy that we just put in, and Unicomp is the Finch, which we also just put in. Everything is mounted in this single cabinet, powered off of the same plugs coming out of the back. It all works 100% perfectly, and this primary cabinet is complete. Talk about a milestone. I did not think we'd get here 2 years ago when we started this. This is epic. Yes! All right. So, well, that's it for this episode. I want to thank you guys so much for watching. I'm going to tidy this up a little bit and get a lot of beauty shots for you. And man, I hope to see y'all in the next episode.